Chapter 3 is a little shorter chapter. I'll start it today, and then next time we'll finish it up, and then we'll be able to even start chapter 4 next time. So it's like half of today and then about half of next time. Vectors are very, very important quantities. Remember, we talked about in chapter 2, there are certain quantities in nature that have a direction associated with them. So examples of vectors: we gave force, displacement, velocity, pressure, ... Remember all those examples we gave. So one of the important things for us, in order for us to do, is to learn how to divide a vector into its components, how to express a vector, how to write a vector, plus how do we add two vectors, or how do we subtract two vectors in order to be able to do that. When we add two forces, okay, for example, if I tell you I push something with 5 newtons of force, and then another person pushes that with 5 newtons of force, what's the total force on it? What's the answer? There's no answer, right? Depends on the direction. Whenever something is a force, you can't simply just add 5 newtons of force, 5 newtons, or 10. No, that's if it's in the same direction, it's 10. If I'm pushing something with 5 and another person is pushing something with 5 in opposite directions, right, then the thing doesn't move. Or if I push at an angle, then that changes the thing. So how do we add two vectors based on their direction? That we got to learn that. Or how do we subtract two vectors? Okay? But if I was just adding scalar, like let's say I have 5 kilograms on a scale, I add another 5 kilograms on a scale, what's the total scale reading? 10. That one doesn't depend on direction, you see? So that's why we got to learn to express a vector. So we use the xy coordinate system, and then we have the general vector, let's say vector A. The vector will usually be written with a capital letter, and there will be a vector sign over it. So that's the vector itself. And it's got two properties. It's got magnitude and direction. So the magnitude is written with kind of like the absolute value sign around the vector, or sometimes you just write it as A without the vector sign. It just means that's the magnitude of A. Okay? And the other property that it has is the angle. You need some kind of angle. It doesn't always have to be defined from the x-axis. It could be defined from the y-axis. Some kind of angle, it could be this angle, or it could be, from anywhere, depending. But typically, the most common way of expressing an angle is with respect to x-axis and goes counterclockwise. That's the most common one, okay? So it starts from the x-axis and goes counterclockwise like that. With two pieces of info, then you have now defined the vectors. Like if I say I'm driving at 30 miles an hour, so let's say I'm gonna give you an example of velocity. 30 miles an hour at 40 degrees. Okay, so that means I'm driving that way at 40 degrees. Two pieces of info is needed to fully describe the vector, right? Now the other two pieces of info we could use is its x and y component. Okay, its x and y component tell us its projections and its projection onto the y-axis. Okay, so that would be this length here, ax, right? And this would be the ax vector, and this will be the ay vector, right? And the magnitude of the ax vector is ax, and the magnitude of the AY vector is AY. So in other words, the sum of these two vectors, AX plus AY, give you A. So AX and AY are the magnitudes of its projection. Okay? Now we could use some trig in order to calculate AX. If I know that the magnitude of A from here to here, if I know that the magnitude of A is A, and if I know the angle is theta, then the magnitude of AX is going to be what? A cosine of theta, right? And if I know the magnitude of A, and if I know the angle, what's AY then? You see? Or if this angle is given to you, let's say alpha is given to you, and theta is not given, you could, if alpha is given, you could first calculate theta, right, because it's a complementary angle, and then use cosine theta, sine theta. Or you could say, instead of using theta, you could stay with alpha. Then what would you need to do? A sine of alpha, yeah, because you got to look at this triangle, right? Sine of alpha is the opposite end, so the x component is the sine of alpha. So the x component is not always the cosine. It depends on which the angle is with respect to what axis. And then the y component will be a cosine alpha. Okay? So if I know the magnitude and the angle, I can get the components by just using this. And then once I get the components, the vector will be AX I hat plus AY J hat. The total vector A can be made up of its two components. AX is the magnitude of the x component times I hat. What is I hat? I hat is a unit vector in the x direction, and its magnitude is 1. So if I multiply AX by 1, I get AX. And then J hat is a unit vector in the j direction, and its magnitude is 1. So that's the complete description of the vector then, AX I hat plus AY J hat. Now, what if I know the components of a vector and I want to get to the magnitude of the vector? How would I go the opposite way? Okay? Let's say, for example, I told you somebody walked 3 miles this way and 7 miles that way. Where did they end up? So in that case, I'm giving you the x and y components of the vector, and I'm asking you to find the magnitude of the vector, right? So from that, if I want to know the magnitude of the vector, I say a squared is 3 squared plus 7 squared, right? And then take the square root. So the general formula will then be A is ax squared plus ay squared square root. Okay? And then the angle, if I want to know the angle, then I need to do what? I could do, if I want, cosine of theta is 3 over a, and since I got a from here, right, I could use cosine of the angle 3 over a and then take the inverse cosine. But usually the one that we do is we do the tangent, because this and this are given. To do cosine, you have to use a, and a is a derived number.